Welcome back to the Organic Chemistry course for undergraduate students. Let me briefly introduce to you the plan of the current lecture. First, we will recall a very important rule from the Inorganic Chemistry course, the octet rule. Based on this rule, we'll talk about the diagrams that show the bonding between atoms of a molecule, as well as the lone pairs of electrons that may exist in the molecule. These diagrams are called Lewis structures, and they are the easiest way to describe a covalent bond. Then, we will take a look at some exceptions from the octet rule. They are not so vital to know how to treat the trivial organic substances, but you will see that later in the course they will become useful. Lastly, we will discuss a very important property of a covalent bond. Spoiler alert, its strength. Let's go! We have seen earlier that there are three major types of bonds: covalent, ionic, and metallic. The covalent bonds lie at the heart of organic chemistry, and there's quite much to understand about them for every organic chemist. As we have previously discussed, the covalent bond is such a bond that is typically formed between two nonmetals. To be more specific, two electrons are usually shared between the nuclei of atoms involved in the bonds. Of course, in order to speak about anything, we need a certain way of graphical representation of it. The same is true for covalent bonds. We need some way to represent these bonds on paper or slide. That's why chemists have developed multiple ways of depicting covalent bonds, and one of the most popular representations is called the Lewis structure. Several examples of Lewis structures can be seen on the screen now. Before discussing it in detail, it is reasonable to refresh some basic knowledge about the atomic structure. As you know, the electrons in an atom can be divided into two subgroups: the core electrons and valence electrons. The core electrons are located closer to the nucleus and thus are held quite strongly. In contrast, the valence electrons are located much farther from the nucleus and, according to previously discussed Coulomb's law, are held most loosely. Here is Coulomb's law once again, and if you don't really understand what is going on here, just check our introductory video to the fundamentals of bonding theories for organic chemists. That's why the core electrons do not participate in the formation of any chemical bonds, whereas the valence electrons are responsible for bond formation. In other words, the valence electrons define the chemical properties of elements. The Lewis structures of compounds and Lewis symbols of elements reflect only the number of valence electrons, while the core electrons are omitted for clarity. Well, it's enough theory, let's run to the practice. On the slide you can see a general structure of a Lewis symbol. It is very simple. In a Lewis symbol, we represent the valence electrons of main group elements as dots surrounding the element symbol. Here you can see the electron configuration of nitrogen. We won't discuss it in detail because we hope you remember such basic material from the high school or inorganic chemistry course. It is obvious that nitrogen has 5 valence electrons, and it's very simple to deduce the Lewis symbol for it. Just count the number of electrons and draw them as dots surrounding the capital N, as shown on the screen right now. Despite it being a very simple material, I would ask you to pause the video and try to write the Lewis symbol of sulfur. Done? Here's the right answer, check yourself. I'm pretty confident that you have managed to do it, and we can move on. Now we know how to draw the Lewis symbol for any atom. From the inorganic chemistry course, we know that many elements tend to form chemical bonds and thus build a compound. But I guess you have heard about the noble gases that either don't form any compounds or do it not so willingly as other elements. Now on the slide you can see several compounds formed by noble gases. I hope you like their structures. The reason for such a behavior is the full outer electron shell of a noble gas. Apart from helium, all of them have 8 electrons on the outer electron shell. You can see their electron configurations on the slide right now. You might remember that this electron configuration is very stable, and that's why all other nonmetals tend to share their electrons with other elements, thus gaining 8 electrons in total. And this leads us to the well-known octet rule. The octet rule postulates that the main group elements tend to bond in such a way that each atom has 8 electrons in its valence shell, giving it the same electronic configuration as a noble gas. To be more precise, a closed shell with an ns2-np6 electron configuration in which n is the energy level number. Okay, now we understand why atoms form covalent bonds. It's the proper time to speak about the Lewis structures. A Lewis structure is a very simplified representation of the valence shell electrons in a molecule. It is used to show how the electrons are arranged around individual atoms in a molecule. Like in the Lewis symbols, the electrons are shown as dots. While drawing the correct Lewis structure of a compound, the goal is to obtain the best electron configuration. It means that the octet rule is followed and also the formal charges need to be satisfied. It is reasonable to look at the octet rule first and then move to the formal charges. Let's try to describe some well-known molecules using Lewis symbols. The first molecule we describe will be HBr. On the right hand side you can see the electron configurations of hydrogen and bromine atoms. So the corresponding Lewis symbols are quite obvious. Hydrogen has only one electron highlighted in pink, and bromine has 7 valence electrons in blue. In the bottom left corner you can see the 2 Lewis structures of the HBr molecule. Both of them are equivalently correct. Pay attention that we have an octet of electrons around the bromine atom. In contrast, a hydrogen atom has only 2 electrons that form the actual covalent bond. Hydrogen doesn't follow the octet rule, remember it. For the sake of simplicity, we can draw a solid line instead of 2 shared electrons. Now you understand the origin of solid lines that represent covalent bonds and structural and skeletal formulas that we have discussed previously. Well, now it's your turn. Pause the video and try to draw the Lewis structure of the O2 molecule. Done? Let's check together your solution. The electron configuration of the oxygen atom is shown now on your screen. The corresponding Lewis symbol is given on the left-hand side of the slide. Finally, the Lewis structure of O2 is given now at the bottom. Pay attention that we have an octet of electrons around each of the oxygen atoms. 2 electron pairs are common, which means that we have a double bond. Let's substitute the corresponding pair with 2 solid lines that stay for a double bond. I hope that everything is clear now. If not, you know where the comments are, and don't forget about the webinars that we organize based on the questions that you leave in the specific threads on our forum. All links are in the description below as usual. Okay, we have formulated the Lewis structures for diatomic molecules. Of course, our next goal is the Lewis structure for a polyatomic molecule. Let's begin with PCl3. Its 3D model can be seen on the screen now. Isn't it beautiful? As usual, we begin with the electron configurations of the constituent atoms. They can be seen on the right-hand side of the slide. Then we move on to the Lewis symbols of phosphorus and chlorine. They can be seen on the left-hand side. Phosphorus has 5 electrons, 3 of them are unpaired, whereas chlorine has 7 in total and only 1 is unpaired. It means that phosphorus can form 3 bonds and each chlorine can have only 1. The corresponding Lewis structures are located as usual at the bottom. Pay attention that we have an octet of electrons around all atoms and some lone pairs. This time I have circled all electron octets with corresponding colors so that you can see exactly how we count electrons. The last thing that we need to do is to substitute shared pairs with solid lines. Now, let's try to apply the Lewis scheme to the polyatomic molecule with a double bond, for example, ethylene. As you might remember from our previous lecture, ethylene corresponds to the class of hydrocarbons called alkenes, and here you can see its 3D structure. In the subsequent videos we will explain why it's planar, so stay tuned. It consists entirely of carbons and hydrogens, and no heteroatoms are present. Now the electron configuration of carbon and hydrogen atoms are shown on the screen. If the carbon atom is in the excited state, we can get this electron configuration, where the carbon atom has 4 unpaired electrons. They are highlighted in blue in Lewis symbol and electron configuration. So the Lewis symbols of these atoms are quite trivial and are shown on the left-hand side right now. Finally, we get our Lewis structure of ethylene, which is located at the bottom. It is obvious that both carbons are surrounded by 8 electrons each in total, meaning that the octet rule is followed properly. The highlights should help you to follow the electron counting. If it's not obvious, pause the video and take your time. At the beginning I have also mentioned that the formal charges shouldn't be taken into account. But what is the formal charge? Actually, it's very simple. The formal charge is the difference between the number of valence electrons of an atom in a neutral free state and the number assigned to that atom in a Lewis structure. Let me show it to you based on two examples. Here's the Lewis structure of carbon dioxide. On the left, you can see the Lewis symbols of carbon and oxygen. Carbon has 4 valence electrons, while oxygen has 6 of them. I have colored the electrons attributed to oxygens in red and to carbon in blue. As you can see, carbon still has 4 and each oxygen still has 6 electrons. If we subtract the number of electrons that carbon has in the Lewis structure and in the free state, we will obtain 0. It means that neither carbon nor oxygen has formal charges. Pause the video and inspect the calculation by yourself carefully once again. Remember that the way you count the electrons for the octet rule and formal charges are different. While considering the formal charges, we count only 1 electron from each shared pair that represents a bond. Well, here's the Lewis structure of the acetate anion. You can clearly see that oxygen is surrounded by 3 electron pairs and forms 1 carbon-oxygen bond. It still has an octet, but the formal charge in this case equals -1. Once again, don't hesitate to pause the video and inspect the calculation carefully. The general rule that you should remember from the inorganic chemistry course is that you should try to formulate such a Lewis structure in which all atoms have an octet rule and the number of non-zero formal charges is the smallest possible. And another important fact about the formal charges. The formal charges should match the electronegativity of the atom. That is, negative charges should be on the more electronegative atoms and positive charges on the least electronegative atoms if it is possible. For example, we should place a formal charge of -1 on oxygen instead of carbon, and +1 on carbon is much better than on oxygen. Here are a few examples. Take your time to inspect them and ask your questions below if anything remains unclear for you. I should also stress the fact that formal charges don't reflect the real charge distribution in a molecule, it's just our model that exists for convenience. Lastly, if we sum up all the formal charges within a molecule, we obtain the real charge of our ion or molecule. Here is the already discussed example of acetate anion. At the bottom you can clearly see how to calculate the real charge of a molecule using the formal charges in Lewis structures. And pay again your attention to the location of the negative charge. It strictly correlates with the electronegativity of the atoms, just as we discussed before. As you have already seen, nothing is perfect, even the octet rule. The octet rule is not valid for hydrogen and helium because there is no 1p level. So for these atoms works 2 electron rule, as you saw in the example with the HBr molecule. It means that hydrogen can have only 1 covalent bond, as it tries to gain 2 electrons in total, just as helium has. Also, the elements in the third row and beyond that, which have d electron level, tend to make hypervalent molecules such as ICl5. Hypervalent compound is a molecule that contains 1 or more main group elements, apparently bearing more than 8 electrons in their valence shells. Phosphorus pentachloride PCl5, sulfur hexafluoride SF6, chlorine trifluoride ClF3 are examples of hypervalent molecules. Their formulas, 3D models, and Lewis structures can be seen on the screen now. There are different opinions regarding the Lewis representation of hypervalent compounds. Some researchers say that it is essential to draw an octet for any atom that is hypervalent. Others tend to be not so strict and allow to draw more than 4 bonds for such atoms as sulfur, phosphorus, chlorine, etc. In our opinion, it doesn't really matter because it's just our formal way of representation. Moreover, it's just a model that has a quite lot of approximations. Nevertheless, let's take a look at the Lewis structure of the hypervalent molecule ICl5. The electron configurations of iodine and chlorine atoms are shown on the right. If iodine is in the excited state, we can get such an electron configuration where the iodine atom has 5 unpaired electrons. So the Lewis symbols of these atoms are shown on the left-hand side of the slide. Red dots in the Lewis structure of iodine represent unpaired electrons. Finally, the resulting Lewis structures of the ICl5 molecule are given at the bottom. Pay attention that we have more than 8 electrons around iodine and octet around chlorine. Of course, we can redraw this Lewis structure by adding formal charges in such a way that iodine and all other constituent atoms have an octet of electrons. As this video is dedicated to the fundamentals of organic chemistry, we will not discuss further the Lewis structures. Of course, there is much more to deal with, for instance 2 electron 3 center bonds. but you will learn it in the inorganic chemistry course. This was just a brief recap of the necessary material that you should have learned during your high school chemistry classes. The last topic for today is the energy of a covalent bond. In the previous video we have seen how the energy of the systems that consist of two atoms depends on the distance between them. Just take a look at it once again. When the atoms approach each other, the energy of the system decreases because atoms share their electrons, thus forming a covalent bond. This energy is released, for example, in the form of heat. If we try to separate atoms from each other, then the energy of the system begins to increase, and it means that we need to supply energy to the system to break a chemical bond. The covalent bond can be treated as broken when the energy of a system doesn't change significantly upon bond elongations. We have just highlighted this situation on the graph. It is also important to note what happens with the shared electron pair during bond cleavage. Obviously, there are two possibilities. Electrons can be distributed equally between two atoms, just as shown on the left-hand side. In this case, we name the process of bond cleavage as homolytic cleavage, and it leads to the formation of two neutral particles, in this case, atoms A and B. In contrast, if both electrons after cleavage are attributed to one atom and the other has gained no electrons from the shared electron pair, then we call this cleavage to be heterolytic. In this case, anion and cation are formed. I should stress out the fact that homolytic cleavage is much more preferable in a gaseous state than a heterolytic one, while in liquid media it's quite complicated to predict the more favorable pathway. I guess now it's time to define the concept of covalent bond strength. We measure the strength of a covalent bond by the energy required to break it. That's the energy necessary to separate the bonded atoms, just as I showed you using the graph with atoms A and B. The stronger the bond is, the greater the energy required to break it is. The energy required to break a specific covalent bond in 1 mole of molecules in gaseous state is called the bond energy or the bond dissociation energy. It is also important to note that in this case we're talking about the homolytic bond cleavage. Remember this definition, because we will use it quite often when dealing with alkanes and their chemical properties. Lastly, let's look at some important bonds in organic chemistry and their energies. The energy of a typical CC single bond is 345 kJ per mole. The energies of double and triple CC bonds are much higher, namely 611 and 837 kJ per mole respectively. It means that every additional pair of shared electrons makes the overall attraction stronger and thus harder to break. While dealing with alkenes and alkynes in greater detail, you will see that bond energies correlate also with the bond length. And how the covalent bond length is defined is discussed in our next video, that's why stay tuned and don't miss any of our upcoming videos. That's it for today. Let's make a brief overview of what we have discussed. We have begun with recalling a very important rule from the inorganic chemistry course, the octet rule. Based on this rule, we talked about the Lewis diagrams that show the bonding between atoms of a molecule, as well as the lone pairs of electrons that may exist in the molecule. Then, we have continued looking at some exceptions from the octet rule. They are not so vital to know to treat the trivial organic substances. Lastly, we discussed a very important property of the covalent bond, namely its strength. If you have any questions related to this video or any other topic in chemistry, biochemistry or pharmaceutical sciences, you're more than welcome to ask them on our website and forum or in the comments below this video. We'll be glad if you give us a like and subscribe to our channel. Thank you very much for your attention, and we'll meet once again in the next video.